Okay, so now we're going to dive a little bit into convergence theory for numerical methods converging to weak solutions of hyperbolic conservation laws, and talk about the Lax-Wendroff theorem and also how you can show that the solution you're converging to actually also satisfies the entropy condition in some cases. And then talk about how that entropy stability, as it's sometimes called, also relates to the sort of nonlinear stability we need for convergence in general, and total variation stability, and how total variation diminishing schemes fit into this. So again, we're looking at methods that are in conservation form, which, remember, you can derive from the weak form of the differential equation that involves integrating the conservation law in space and time. Or another way that we've looked at it is that you can take the differential equation, multiply by a smooth test function that has compact support and vanishes out away from the real line and outside of some finite interval in space. And if you multiply by phi and integrate in space and time and then do integration by parts, you can move the derivatives from the function q, which might be discontinuous, onto the smooth function phi, and that gives you another way of defining what we mean by a weak solution. So far we haven't done much with this, but we're going to use it today to prove the Lax-Wendroff theorem, or at least sort of outline how the proof goes. So the proof, or the theorem, says that if we use a method that's conservative and if it's consistent with the conservation law in the sense that the numerical flux function, assuming that we're looking just at the three-point scheme, then the numerical flux function would depend on two states, qi minus 1 and qi, to give you a flux fi minus a half that comes into our flux differencing formula. If that's consistent in the sense that if the two states are the same, then this should just simply reduce to the flux of the conservation law. And we also need some Lipschitz continuity as the two states approach q bar. If that's true, and if we have a sequence of numerical approximations as we refine the grid in space and time that is converging to some function as we refine the grid, then this function that we're converging to has to be a weak solution of the conservation law. Okay, so this theorem by itself doesn't say we will converge. For that, you need some form of stability. And it also doesn't say that we would converge to the physically correct solution in the case where the weak solution might be non-unique. For that, you need some sort of entropy condition. So we'll look at those things too as we go along here. But the basic idea of the theorem at this level is just that if we are converging to something, if we've used a consistent conservative method, then we have to be converging to a weak solution. So we can't, for example, be converging to a discontinuity that's in the wrong place. We can't be looking at, say, a Riemann problem that should have a shock moving at some speed and have a numerical method that's converging nicely to a discontinuity moving at some different speed, as we saw is possible if we use a non-conservative method. So how do we prove this? Well, we'll start with this conservative numerical method, and we'll do the same sort of thing that we did to take the differential equation and compute the weak form. We'll take capital phi ij to be an approximation of a smooth test function phi that has compact support and some smoothness properties. And then we'll just multiply by phi in everywhere in this difference equation, both on the left and the right. And then in the differential equation, what we did after multiplying by phi was we integrated in space and time, and then we did integration by parts. So we're going to mimic that here. We're going to take this equation for each in, and we're going to sum over all I and all n, mimicking integrating in space and time. And because phi has compact support, these phi in's are going to vanish for I or n sufficiently large. So I've written these as infinite sums, but there's only a finite number of non-zero terms in each of these sums. And then we're going to use summation by parts to transfer the differences from the q's. So here we have differences of q at two different times. Here we have differences of f at two different spatial locations. We can do a summation by parts that's analogous to integration by parts to convert those into differences of the smooth phi function. So if you're not familiar with summation by parts, it's a good trick to have in your tool bag if you work at all with finite difference type methods. So integration by parts formula you're all familiar with, that's at the top here. To look at a summation by parts, let's look at a sort of analogous sum. So sum of ui times vi minus 1. And if you wanted, you could divide by delta x to make that look like a derivative of v, but then multiply by delta x to make it look like an integral rather than just a sum, but those two cancel out. So I'll just leave those out. And then the idea is if you take that sum and you just write out what it is term by term, and you start rearranging the terms so that rather than being a value of u multiplied by a difference in v's, instead we try to write it as a value of v times a difference in u's. We can look, for example, at where v1 appears here, it multiplies u2 and it multiplies u1 with opposite signs. So if we just rearrange this sum, we can write it in the form here, where we've written it basically as a sum of v's times differences in u, except there's a couple of boundary terms that don't quite fit that pattern, which are analogous to the boundary terms that come out in the integration by parts formula. So all of the other terms, except for those boundary terms, we can write as a sum of differences in u times v values. So that's the summation by parts formula. So again, we want to apply it now to prove the Lax-Wendroff theorem. So we've taken our difference equation, we've multiplied by phi, we've summed over space and time, and now we'll apply that summation by parts in the sum. The first sum, we'll apply it on the sum over on the sum over n, because it's differences in n and n plus 1 and n. So that's like integrating by parts in time. And over here on the right, we have differences between I plus a half and I minus a half. So we'll apply the summation by parts formula to that sum. And when we do that, what we end up with looks like this. And I guess I've thrown in some delta t and delta x terms, so it looks more like the derivative of phi times q I in the first double sum, and the derivative of phi with respect to, this would be like an approximation of the derivative of phi with respect to time. This is like an approximation to the derivative of phi with respect to x. And that's very analogous to what we have in the integration by parts formula, where we had d phi dx multiplying q and d phi dt multiplying f after integrating by parts. And again, the idea is that this phi function is smooth, so these differences in phi, as we refine the grid, should really be converging in the strong sense to derivatives of phi. And so there's a lot of details in actually completing this proof, which I'm not going to go through, and they're sort of only briefly outlined in the book, but the idea is that what you can show if you take the limit properly is that as you refine the grid, if this sequence is converging to some function, then the function must be satisfying the integral that defines a weak solution, because these sums converge to those integrals because of the fact that phi is smooth enough. Of course, there might be discontinuities in the resulting solution if there's a shock wave or something, so we might not have pointwise convergence right at the shock wave, but you can show that almost everywhere as delta x and delta t go to 0, or if you're converging almost everywhere as delta x and delta t go to 0 to some function, then that q must satisfy the integral form of the conservation law, the weak form, which is what we get in the limit here. And in doing that, in addition to the fact that the differences in phis are converging to derivatives, and that we're assuming that the qin is approaching some given function, we also have to be assuming that these fluxes fi minus a half n are converging to the appropriate flux f of qi. As we refine the grid, the values of q left and q right at each interface are very close to each other, almost everywhere at least. Again, there might be isolated discontinuities, but almost everywhere we should expect that the two states are converging to the same value, and the flux should be converging to little f, the flux of the differential equation at that common state. So that's where the assumed consistency of the flux function comes into this proof. If the numerical flux was converging to something else, then you might be converging to a solution of a different conservation law, of course. And also, when you look at the details, you actually have to use the Lipschitz continuity of f to make these arguments that that you can really expect convergence in this form. But that's the basic idea of the proof of the Lax-Wendroff theorem. Well, it turns out we can do something similar for the entropies. So the Lax-Wendroff theorem by itself only says that if we're converging to some function, it's some weak solution, but it might not be the physically correct solution. So in the last lecture, we looked at what happens if you define, if you want to prove that you're converging to the right solution by defining an entropy function eta, a convex function of Q, and the corresponding entropy flux psi of Q. And then you have a discrete, or you have a differential equation in the weak form that instead of the differential equation for Q has an equality, but the differential equation for eta, we had d eta dt plus d psi dx is less than or equal to 0 in the weak sense. And so we would like to show that if we have a numerical method, then we're converging to a solution that satisfies this entropy condition. And it turns out you can do that if you assume that for whatever numerical method you're working with, there's also a numerical entropy flux that's consistent with the flux psi in the entropy condition you're trying to look at, in the same sort of sense that script f is consistent with little f. This capital psi should be consistent with the little psi in the differential equation. And if you can show that for the numerical method, the entropy evaluated at the new state qin plus 1 is less than or equal to the old entropy minus the difference, flux difference of the entropy flux based on this numerical entropy flux. If you can show that that's true, then you can apply the same sort of idea that we used for proving the Lax-Wendroff theorem to prove that you also have the entropy condition satisfied in the weak form in the limit. So again, you would multiply by a test function phi, sum it up, use summation by parts to move the jumps in eta of Q and psi of Q onto jumps in phi, and then look at the limit as you converge. And what you can show then is, assuming this is satisfied, that if your numerical approximations are converging to some function, then that limiting function also has to satisfy the weak form of the entropy condition. Again, it doesn't necessarily guarantee that you converge. You would still need some sort of stability condition for that, but it can say that you are converging to the entropy solution. And in some cases, that entropy condition can serve as a form of stability that also allows you to say, in fact, you are converging, but that's not always true. We'll talk a bit more about that later. But let's look at Godunov's method in particular and show that for Godunov's method, we do have this entropy consistency, and we can in fact show that we would be converging to the correct weak solution with the correct rarefaction waves, and we can't possibly converge to a solution with entropy violating shocks if we use Godunov's method, assuming that we use Godunov's method with the entropy fix or with the correct entropy solution in each time step. So in Godunov's method, we can think of solving all the Riemann problems and then averaging onto the cells, or solving the Riemann problems and using that to define fluxes at the interface. Either way, we have to use the correct Riemann solution in each of those time steps in order to get this result. But assuming that we've defined the interface flux to be f of this Q Riemann, what comes out of the Riemann solution between these two states. So if it's a rarefaction wave going this way, then the value at the cell interface would simply be the value in the left state. But if it's a transonic rarefaction wave, for the waves are spreading out here, then for this Riemann solution, we would have to use the appropriate value f evaluated at the sonic point in order for this result that we'll be talking about to be true. But assuming that we use the correct entropy satisfying function to define our Q at I minus a half and the flux based on that, then we can look at the entropy condition, and we can simply define the capital psi at I minus a half to be psi evaluated at the value along the interface. That's how we'll define our entropy flux for the numerical method. And then, again, as usual, we'll let Q and tilde be the exact solution of the conservation law, starting with the piecewise constant data, and assuming that by exact solution I mean the entropy satisfying exact solution that has rarefaction waves if necessary. And then if we do that, then we can simply integrate the entropy equation that we know holds for the true solution, namely, again, the equation eta t plus psi x is less than or equal to 0 in the weak sense. We know that holds for our weak solution q tilde n if we've respected the entropy condition in solving each of the Riemann problems. So that means that if we apply that to this function over one time step, then we can say that the integral of this entropy at the advanced time is less than or equal to the integral at the original time as modified by the integrals in time of the flux at the two boundaries. That's the one integral form of the entropy condition. So assuming q tilde n is the entropy solution, then that's true. But now what's nice is that this value q Riemann at I minus a half is constant, and therefore this entropy flux is constant in time. So this integral in time is just turns out to just be the constant value times delta t. Similarly here. And also our initial data at time tn was constant in space over each grid cell. So these integrals here we're also integrating something that's constant in space. So that means that the right-hand side simply reduces to, this integral just reduces to eta of qin, since q tilde is constant in the cell, and each of these integrals reduce to delta t times the constant value along each cell. Similarly here, delta t times the constant value along that cell. So let's get rid of these intermediate steps, and what we have then is what's shown up here, that the cell average of eta of q tilde is less than or equal to just eta evaluated at the previous cell average minus delta t over delta x times the difference in this entropy flux at the two boundaries. Now the problem with that is that that's not quite what we want. What we really want is that eta at the new cell average qin plus 1 is bounded by what's on the right-hand side there. But all of these other terms, we could see that the solution was constant in the integrals, but that's not true here. This is the solution at the end of the time step after we've solved Riemann problems at each interface and then averaged q at the new time level. So this qn tilde at the new time level is not constant in space. And now we're evaluating eta at each point and we're averaging that value. So that's not necessarily the same as eta evaluated at the cell average of q. So what we need to complete the proof is just to show that eta evaluated at the cell average is in fact less than or equal to the value we had on the top left there. And then we'll have what we want. And it turns out that's true because in general, since eta is assumed to be a convex function, there's something called Jensen's inequality that says for any convex function for which eta double prime is greater than or equal to 0, the value of eta of q evaluated at the average value of q of x is less than or equal to the average value of eta of q of x. In other words, we have exactly the inequality we need to complete this proof. So again, it's important here that our eta function is a convex function. So this shows that Godunnov's method actually converges to the correct solution, provided it's converging at all, and provided that we've implemented it with the entropy fix so that we're using the correct solution to each set of Riemann problems. But again, this doesn't necessarily imply that Godunnov's method converges. And of course, if we take the Courant number greater than 1, for example, and refine our grid, then we know it won't converge. So we need some form of stability in addition to this. So let's just step back for a moment and just briefly review sort of the relation between stability and convergence more generally. So if we let little qn be the cell averages of the exact solution at some time tn and capital Qn be the numerical approximations we're computing, then we can look at the numerical approximation as being sort of the exact values plus some error in each cell. And this would be what we call the global error, E sub n, at time n. And if we apply some generic method to compute qn plus 1 as some function of qn, assuming we're just doing explicit time stepping as we're looking at, then we can look at the numerical method applied to qn as being the numerical method applied to qn plus en from this equation up above. Or we can also look at, now if we subtract off the true solution at time n plus 1, we can compute the global error at time n plus 1 as that difference. And if we replace qn plus 1 by the numerical solution at little qn plus en, and then add and subtract the numerical solution of the true, or the numerical single numerical step starting with the exact solution, taking one step of the numerical method. If you add and subtract that and rearrange a bit, then we can write that as the difference between n, the numerical method applied to data qn plus en, and the numerical method applied to just the exact solution qn. And then this other term here we can call delta t times the local truncation error, or delta t times tau n is what we often call the one-step error. So this is the new error that's been introduced in this step, but what we have here is sort of the effect of all the previous errors encapsulated in the previous global error en, and the fact that when we take a time step on qn plus the accumulated errors, that's different from taking a time step on the true solution. Whereas the local error, which is often derived by doing Taylor series expansions, is just looking at a single step and saying, if we start with the true solution at time n and apply the numerical method to that, how does that differ from the true solution at time n plus 1? So we can split it up into the local error we're introducing at each step and the effect of the numerical method on the accumulated error en. And so there's that equation again. And so if we take norms and use the triangle inequality, we can bound the norm of the new global error in terms of the norm of the difference between n, the numerical method applied to qn plus en, minus n applied to qn, plus the delta t times the norm of the truncation error. And so if we have a bound that says that this difference is less than or equal to the norm of the previous error, then we could put that into here, and we would end up with bounding the norm of en plus 1 in terms of the norm of en plus the new local error. And in that case, you could just kind of iterate this, and every step you'd just be adding in a new local error and accumulating those. And so if we sum that up over capital N steps, we could eventually work back and get a bound on the global error after capital N steps in terms of whatever the initial error was, the error in our initial conditions, plus delta t times the sum over each step where we introduce a new one-step error. And so that says that our global error would be bounded by the initial error plus something that looks like delta t times the number of steps is, say, some time capital T that we're trying to approximate the solution at. And as long as n times delta t is equal to that time, we can replace this sum by just n times delta t, which is capital T, times some global norm of the truncation error over the entire computational domain and time period that we're integrating things. So that gives us a bound on the final global error that will go to 0 as we refine the grid, provided that we're approximating the initial data well enough that the initial error goes to 0, and provided that the local truncation error goes to 0. So if it's what we call a first-order accurate method, then we expect this norm of tau to go to 0 like order delta t. So these terms would all be going to 0, and we would have convergence. And you can allow even a little bit of growth in here. You could put a factor of 1 plus some alpha times delta t, and here you could allow a little bit of growth each time step as long as it's bounded by some constant times delta t, and then you get similar bounds, but with factors of e to the alpha capital T coming in, which you can see in this section of the book if you want more details. But the point is that in order to go from the sort of the local truncation error that we can compute using Taylor series to this bound on the global error, we need something like this inequality here. And this is really the stability condition, if you will, the fact that we need to be able to bound the effect of the numerical method on some perturbation of the true solution in terms of the size of that perturbation. And if the method is linear, which means that the numerical method applied to a grid function that's qn plus en at each grid point gives exactly the same thing as if you applied a numerical method to qn and then applied a numerical method to en and add those two together. That's what we would call a linear method. If that's always true, then if we put this into here, then the n of qn's drop out, and we end up with exactly what we want. Or we end up with just the condition that the numerical method applied to any set of global errors en should be bounded by the norm of that en. So if we had this condition satisfied, then we would be able to show that the method is stable and converges. But if the method is nonlinear, that's not necessarily enough. We can't do the same manipulation if it's nonlinear, and we really need something more like this contractivity condition that says that if we apply the numerical method to any grid functions p and q, then the difference between those is no bigger than the difference between p and q before we applied the numerical methods. That's what we're looking at here, where p is qn plus en and q is just qn. So we need contractivity rather than just this sort of bound on the growth of the numerical method itself in one step. So one observation is that this entropy function we've talked about is like a quadratic function in many cases. And so this sort of entropy stability that we've been talking about, or the fact that this entropy condition is satisfied in the form we used for proving that we satisfy an entropy condition if we're converging to some weak solution, that you can look at as saying that the entropy of the numerical solution after one step is no larger than the entropy of the previous step, as modified by fluxes at the boundaries, for example. And that's because eta is a convex function. That's a lot like saying that the norm of n of q is no bigger than the norm of q. But unfortunately, that doesn't always imply contractivity, and so that's not always enough in order to prove the convergence that we want. In some cases, that is enough. There's a famous theorem of Khrushchev from 1970, looking at scalar conservation laws, who showed that if you have entropy stability for a large enough set of entropies, for all convex entropies, or what he did actually was to look at entropies of a very special form here called the Khrushchev entropy, where eta of q is the absolute value of q minus k for some fixed number k. So these aren't even convex functions in the form that we've been talking about, because if we look at this as a function of q, it's actually piecewise linear with a jump discontinuity. So if we look at the second derivative of that, it's 0 everywhere except at that jump discontinuity. It's really a delta function. But what he showed was that by looking at these sort of limiting cases of convex functions, where the second derivative was just a delta function at an arbitrary point k, if you had entropy stability in the form here for all of these entropies, then you could in fact show that you have entropy stability for any convex entropy. You could use these delta functions to sort of build up a more general convex function. And so the entropy flux for this particular entropy turns out to be this function here, f of q minus f of k times the sine of q minus k. And so if you can show that your numerical, or well, actually he was showing this originally for differential equations, if you can show that your differential equation satisfies this entropy condition, that the time derivative of this entropy plus the x derivative of the entropy flux is less than or equal to 0 for all constants k, then in fact you could prove that the solution of the PDE is contractive in the one norm, that the one norm, the integral of the absolute value, at any time t, if you look at two different initial conditions, q and w at time 0, as different functions of x perhaps, then the one norm of the difference between q and w at any later time is always bounded by the one norm of the difference between q and w at the initial time. So that's called one norm contractivity, and if that's satisfied, then that is enough to pick out the unique entropy satisfying weak solution of the differential equation. And in this case, that's enough also to prove that you have entropy stability of your numerical method in a form that you can turn into contractivity and actually use to prove convergence of the numerical method. So in particular, this approach can be used for Godunnov's method. You can show that for Godunnov's method, the proof I went through that Godunnov's method was consistent with the entropy condition, it didn't rely on any particular entropy. I just assumed it was some convex function. So it was true, in fact, for all convex entropies, and it's also true for these Khrushchev entropies. And so based on this, you can actually prove that Godunnov's method is converging for a scalar conservation law, provided you solve each of the Riemann problems correctly. You will converge as the grid is refined to a weak solution of the conservation law that also satisfies the entropy condition. So that's a very nice result for Godunnov's method. For the case of scalar nonlinear problems, unfortunately, it doesn't extend so well to systems. And moreover, when you look at this condition more generally, it turns out that numerical methods that satisfy this kind of contractivity condition are generally at best first order accurate. You can prove some rigorous things about that as well. So it works for Godunnov's method, which is first order accurate, but it doesn't allow proving convergence of some of the high resolution methods we'd like to look at. So there's another notion I'll briefly mention, which is called total variation stability, which is again related to the TVD methods that we've looked at and the TVD limiters that we've derived. But a little more generally, instead of being total variation diminishing, you can talk about a method being total variation bounded if it has the property that the total variation stays bounded by some constant r for all time up to some time capital T as you refine the grid. So as we refine the grid, delta t might go to 0 and n might go to infinity, but this, as long as we only go up to time capital T, then we should have some uniform bound on the total variation. Of course, what this number r is will depend on how big I choose time, perhaps, and it might depend on what particular initial data I have. In particular, you would expect the total r to be at least as large as the total variation of the initial data. Otherwise, this bound wouldn't even hold at time 0, but it could be allowed to be larger than the total variation of the initial data, but we should have some constant for which this is true up to time t. So a sufficient condition would be if we have the total variation at each time step, if we could show that that's bounded by the total variation at the previous time step multiplied by some factor 1 plus alpha delta t, where alpha is independent of delta t, then as delta t goes to 0, we could iterate with this and see that we get the final total variation is bounded by e to the alpha t, the alpha capital T times the total variation of the initial data, for example, would come out of this sort of bound. A TVD method that we've looked at before is an even stronger condition. It says the total variation at time n plus 1 should be no greater than the previous total variation, in which case alpha is 0 here, or you can drop that exponential factor, and r would be just the total variation of the initial data. But you can relax the TPD condition and still have a method that's total variation bounded. So total variation is a very convenient thing to look at. We've seen it's convenient in terms of trying to guarantee that our numerical solution doesn't develop oscillations that might not look nice, but also you can use it to prove convergence. And the reason is that if you look at the set of functions like the one written down here, the set of all L1 functions for which the total variation of V is less than some constant R, and the support is contained in some interval, so compact support, then this set of functions is a compact set, which means that if you take any sequence of functions that all lie in this space, then any such sequence has to have convergent subsequences. It has to have sequences that converge to something or other, some function. And we can use that actually together with the Lax-Wendroff theorem to prove that we can actually get convergence of numerical methods provided that they satisfy this total variation stability condition. So if we suppose that the method is total variation bounded and it's conservative with a consistent flux, then the theorem is that as we refine the grid, our approximations Qn must be getting closer to the set of weak solutions of the conservation law, defined by this flux F that we're consistent with. Again, here I haven't said anything about entropy conditions, so there might be more than one weak solution. It doesn't say which one we're converging to, and some approximations might be close to one, and if I change the grid slightly, it might be close to a different one, so we can't necessarily say our approximations are converging to a function, but we're converging to the set of weak solutions in that the norm of the difference between Qn and some weak solution is going to 0. And again, I won't go through the proof in detail, but the basic idea is that if this weren't true, then you could choose a sequence of approximations as you refine the grid that are not converging to a weak solution, meaning that they're all bounded away from the set of weak solutions by some positive constants. No matter how small you make delta t and delta x, you're always some distance away from the set of weak solutions. But if you can do that, then, and if you can keep doing that as you reduce delta t and delta x, then that gives you an infinite sequence of functions. And because they have bounded total variation, that infinite sequence of functions lives in this compact space, so we know it has to have a convergent subsequence. So from this set of functions that were, or set of approximations that were not converging to any weak solution, there must be within that some subsequence that is converging to something. Call that function q. So now we have a sequence, if we just look at that subsequence, we have a sequence that's converging to some q using a method that's both conservative and consistent with the flux. And if we have a set of such functions converging to some function, then by the Lax-Wendroff theorem, that q has to be a weak solution. But that's a contradiction to what we supposed when we constructed this sequence of approximations. So in fact, we conclude that we are converging to some weak solution as we refine the grid. So that's the basic idea. There's a bit more in the way of details in the book. And then finally, let's just kind of bring it back to how we look at things in practice in terms of accuracy of methods. As I've mentioned, the total variation bounded is a little more relaxed than TVD. So if we have a TVD method and it's conservative and it's consistent with a flux, then this proof tells us that it will be a convergent method. But also, TVD methods can be useful in getting somewhat better accuracy than TVD methods. So we've looked at how we might construct a TVD method by taking, here I've taken a function Q in red, and I've computed the cell averages, which are the blue dots, and then reconstructed a piecewise linear function using the min-mod limiter in this case. And to reconstruct something that doesn't exceed the total variation of the cell averages that I started with, I have to make the slope flat in these two cells. If I try to approximate the fact that the actual underlying function has a peak there by putting in some non-zero slopes there, then I would have increased the total variation of my reconstruction relative to the original cell averages. And if I were using, say, induction algorithm where that just shifts over, say, half a grid cell, and then we average it back onto the grid, that would introduce a new cell average that's greater than the previous cell averages, and so that sort of method cannot be total variation diminishing. And so a TVD method sort of has to clip off maxima, and as a result, when you have smooth extreme points, these limiter methods typically flatten them out a little bit. And if it's a smooth function, then it should be clipping it by only about order delta x squared in each time step, but still once you take order 1 over delta t time steps to get up to some fixed time, you can lose 1 order there, and you end up with first order accurate global errors. So near extreme points, TVD methods are often looking only first order accurate. So there's a number of other approaches that have been developed over the years to try to improve on that by looking at what are called TVB methods that maybe only require that the total variation in each step be less than 1 plus something times delta t times the previous total variation, or there's a class of methods called essentially non-oscillatory or ENO methods or WENO methods, weighted essentially non-oscillatory methods that also try to sort of get higher order accuracy near extreme points by relaxing this condition, but still getting a method that you can prove is convergent. But actually, even the TVD methods tend to look pretty good, even if we just look at sort of the order of accuracy, or how they're behaving in situations where we might want to be computing in practice. And really, the order of accuracy isn't the only thing you should think about. So I just want to stress that as the final point here. So when we talk about order of accuracy, what do we mean? Well, we mean that the global error, this E sub n, in some norm, should be bounded by some constant times delta x to the s power if it's a method of order s, plus some higher order terms. Typically, when you do a Taylor series expansion, there'll be terms that are order delta x to the s plus 1 and higher perhaps. But there's a lot hidden in this constant and these higher order terms. The constant, of course, it depends on exactly what problem you're solving, but it also depends on what method you're using. And it could be that a first order accurate method with a very small value of c looks a lot better than a second order accurate method with a large value of c, at least on coarse grids. Of course, if c is fixed as you refine the grid, then eventually the second order method will look better. But on the sort of grids we might want to use in practice, it's completely possible that the first order method looks better than the second order method. And similarly, these higher order terms, as delta x goes to 0, they go to 0 faster than delta x to the s, so they disappear. But on the sort of grid we might have to use in practice, they might be actually dominating. So one shouldn't just look at the order of accuracy as the only way, at least, to judge a numerical method. So here's an example we looked at before, a wave packet that's propagating under the induction equation with periodic boundary conditions. So at time 1, it should have just returned to the initial conditions, which are shown in red. And on the left is the Lax-Wendroff approximation to that. And you see that, well, even Lax-Wendroff loses something near the peak because it's such a coarse grid that it's lost accuracy. Whereas I think this was the monotonized centered method used on the right here, it's lost a little bit more. But if we refine the grid and took a much, much finer grid, we would see that the Lax-Wendroff peak is being approximated to order delta x squared, whereas the one on the right would converge only at rate delta x. So on a fine enough grid, the one on the Lax-Wendroff method might look better. But there's other criteria too. So for example, here you can see the shift in Lax-Wendroff, that things have shifted a little bit from where they should be because of the dispersive nature of Lax-Wendroff. And as we've seen, if you take many revolutions, this wave packet can end up in completely the wrong place and not really be approximating the solution at all well. Whereas the limiter method, the blue dots, we've lost some amplitude, but they're really sort of right on top of where they should be. And even if you take many revolutions here and the solution has decayed quite a bit, it's still in exactly the right place. And so for some applications, it's much more important to have your waves in exactly the right place than to have exactly the right amplitude, perhaps. So that's another consideration. And even if we just look at the order of accuracy by taking, say, the one norm or the max norm of the error and refine the grid and see what happens, it might be that that the high resolution method is actually better than Lax-Wendroff. So here's a convergence plot for that same sort of example. It's hard to read here, but on the left is the max norm. So this is the max norm of the error, which is just the maximum over all the grid points, and on the right is just the one norm of the error, summing up the absolute values, multiplying by delta x. And what you see here, this line of slope 2, this is a log-log plot. So if we take the log of the error, we expect the log of the error to go like s times the log of delta x. So if it's a second order method, the log of the error should go like, well, minus 2 times the log of delta x. Sorry, 2 times the log of delta x. This is the slope that we have here. And what you see, the solid line here is the actual Lax-Wendroff method, and so that is in fact converging at rate 2. If we look at the max norm, which would be, for this particular problem, it's really the error right at the peak that's worst. So this is really kind of the error in that peak amplitude. And we would see that as we refine the grid, Lax-Wendroff converges at order delta x squared, whereas the limiter method is converging at a slope that's more like first order. If I draw in the first order slope here. On the other hand, let me clean this up here. On the other hand, where these two cross over is at about 2,800 grid points for this one-dimensional problem. So in practice, we would probably never use that many grid points in one dimension. Certainly when we're looking at 2- or 3-dimensional problems, we wouldn't want to be using that many points in each direction. So if we're only using a more modest number of grid points, and we're up in here somewhere, then the MC limiter method actually looks better than Lax-Wendroff, even though it's not formally second order accurate. And if you look in the one norm, things look even better for the MC method. The max norm, again, is sort of focusing on this maximum that we know is getting clipped off, whereas the one norm is averaging the errors over all points. And in the one norm, even the MC limiter seems to have slope 2. So I'll just leave you with that as the final message here, that even the TVD methods can be very effective and better than formally second order methods, even if they in principle are only first order accurate.